Okay, Assalamualaikum and good morning. So today again, uh, due to unusual circumstances, I'm doing this from home, essentially. Uh, right. We'll continue with the lectures on the whiteboard. As I said, I'm a bit slow in typing things up. So today, let's just recall what we did. I hope I can do this. Oops. Let's recall what we did was to look at essentially partial differentiation and total differential before this. Partial differentiation and total differentials. So that was from was yesterday's, right? Yeah, or the day on Monday, sorry. So today we'll continue with this, but we'll look at several different things, which again are related to partial differentiation, the differential. So one of the things that we want to look at is implicit differentiation. So what seems to be the problem usually is normally we assume that probably you have something like this. Z is given by a function of x and y, then you almost immediately can see that I can calculate the z dx by simply taking the partial differentiation of the f dx, and z dy will be the same. Okay, so given that you can always write functions explicitly, say all the total. So here assume you can put dependent variables on one side. Sorry about the handwriting because I'm writing on this on my knee. Okay, I don't have a table at the moment. Dependent variables on one side of the equation, and then and independent variables on the other side. So sometimes what's going to happen is that you have generally one could have variables, okay, independent or not, dependent or independent, written in one single equation, written in one equation and not separated. Okay, so in this case, what is needed is essentially the implicit differentiation. So let us just, so I'm just giving you the context first. Where do you want to use this? So now we look at examples, several examples, and then we can see how it works. Okay, so here's the example given from the book. So I'm just going to write down the equation first. X plus e to the x equals t. And the question is find dx dt. So this one seems okay, maybe I should not have written it in the way I mentioned above, okay, because it seems like here, okay, the dependent variable is actually on one side of the equation and the independent variable is on the other side. But now is the independent variable is being written in terms of, sorry, which is which now? The dependent variable. This is the dependent variable is written in terms of the independent variables. Did I say that right? Okay. So let's just recall that. So in this case, x and y is your independent variables, and z is your dependent variable, right? So so here, when you write dx dt, you're assuming that one could have written this as this kind of function. Okay, but now you don't have that. Okay, instead you have a mixture of here, if it's individual terms, then x, let's suppose, okay, let me just mention why this is a bit more complicated than what I mentioned above. Here, if I just simply have x equals to t, then this is a linear function of t. Okay. Then if I write ex equals to t, then I can say that your x is a logarithmic function, log function of t. If I separate it out, okay, this is separated. But now you have them together, okay, because when you have them together, then you cannot simply sort of have these two different functions together and then try to find the dx dt. So what one does instead is to differentiate the whole equation. So differentiate the whole equation. So in this case, we want it to have a differentiation with respect to t. So we differentiate the whole equation with respect to t. Okay. So in this case, I have x, which I do not know how to write it as a function of t yet. So what do? Differentiate x with respect to x first, and then differentiate x with respect to t. So that gives me a dx dt. And then differentiate this with respect to x first, and then differentiate x with respect to t. That will give me e to the x dx dt. And t differentiate with respect to t is just equals to 1. Okay, so there you can see that, okay, I can rewrite this equation, collect the terms having dx dt on as a common factor here. So dx dt, this is 1 times dx dt, and then this is ex times dx dt. So and this will actually give us then, okay, dx dt is just simply equals to 1 over 1 plus e to the x. Okay. So okay, that seems simple enough. But the example in the book goes on to ask what is second order derivative. So again, one does not have an explicit expression of x as a function of t. Okay, even if we have already found out what this is, okay, we still do not know unless you integrate this. Okay, unless you integrate this and then find the function x as a function of t, then no, you still can't do it. Okay, you still can't do the way we normally do it. Okay, so what do we do in this particular case is now look at this equation and differentiate with respect to t again. Okay, so in other words, what we do, we take d dt of dx dt plus e to the x dx dt, and then of course on the left hand side it's just constant, then you'll get that to be equal to 0. So let me just push this thing up. So in this case, let us just differentiate it. So then here you just have the second order derivative, which is the thing that we want. But then over here there are two factors here. So again you use the product rule. So the first one you differentiate with ex with respect to t will give you ex again, dx dt. And then remember that this dx dt is coming from e to the x. So I will have to multiply dx dt again as the other factor here. And then the next thing that we need to do is, okay, just now we just differentiate e to the x. Now we differentiate that. So we get plus e to the x, which is the factor that we leave behind over here, and then differentiate dx dt, then you get d to x dt squared, and on the right hand side is just going to be 0. Okay, so you can see now, okay, I still need to simplify this. So for example, here I would have 1 plus e to the x. Let me see. Yeah, 1 plus e to the x d to x t squared, and then I can bring it on the other side. So this is minus e to the x, and then this multiplied by itself, then give me the x dt square. But the x dt you already essentially have already calculated that. So this will give me e to the x times 1 plus e x square. Yeah. So now, okay, this part is equal to that. Okay. Then I now just simply factor this out. Okay. So maybe I'll just rewrite this on another line. So this is minus e to the x, and then bringing this on the other side will go to the denominator. So then I will have 1 plus e to the x cubed. Now if we want to go to even higher order, then one really has to take the derivative of this equation. Okay, so so it gets complicated after a while, but the essential idea is one can use this implicit differentiation to get the derivatives. Okay. Okay. The other thing. Okay. Yeah. Sometimes one do not need the general expression. Okay, so sometimes general expression is not needed. So, but instead, you are given values. Given values. So in this particular case, for example, the values given in the book is x equals to 0 and t equals to 1. So what do you do in this particular case if I want to have the first order derivative at these values? Okay, then I would just simply use the expression given above. Let me just go back. So I will have this equation over here. So let me just can I do this? Maybe I should try to do this. Oops, not that. I want that. Sorry. I want to copy the whole thing. So it's too far away. Sorry. Let me try to copy this. Oops. How do I copy? Okay, it's just too hard. Maybe I'll just, okay, let me just rewrite this. So I'm going to substitute the values inside this equation. So let me go down. So what do I have just now? It was dx dt plus e to the x dx dt equals 1. So I substitute x equals 0 in this particular term. Remember that you don't substitute x equals 0 in the derivative, because we do not know how dx dt looks like. So the one that's you are allowed to substitute the values are these functions, because this function is given it's given as that. Okay, this we do not know what the function is. So in other words, what we have in this particular case, we will have dx dt plus e to the 0 dx dt equals to 1, and that tells us, okay, this is just 1, so that means dx dt is equal to half. Okay, so similarly, if you want to do it for the second order derivative, you just do the same idea. So what we have just now was, let me just rewrite it over here, second order derivative with x equals 0, t equals to 1. So what do we have for the equation is the following. Let me just rewrite it. Sorry, I'm just looking at my notes. d2x dt squared plus e to the x dx. Sorry, this is second order derivative plus e to the x dx dt squared equals to 0. Okay, so again, you don't substitute your x equals 0 inside any derivatives for that matter. So in this case, you can do it here, you can do it here, you can do it here, but you can do it in this exponential here. So that will give me d2x dt squared plus d to x dt squared, because e to the 0 is 1, and similarly over here this is dx dt squared, whole thing squared. But now I already know what dx dt previously, so I can just substitute the values. So that gives me 2 d2x dt squared plus a half square. In other words, what do we have? d2x dt squared. So this is 1 over 4. Okay, bring it on to the other side will give you minus sign, and then divide by 2, that will give me minus 1 to the 8. Okay, so that's a pretty simple equation that one can try to do implicit differentiation. As I mentioned earlier, sometimes you don't have the expression that you need, then you try to differentiate the whole equation altogether. Okay, so let's look at another example which is a bit more physical in this case. You are given this curve x cubed minus 3y cubed plus xy plus 21. So this is a curve. Okay, essentially it's a cubic curve, but you are not able to express in a clear fashion how x is a function of y or y is a function of x, because they get mingled up in this single equation here. So again, what do one do in this particular case? Okay, the question, okay, let me write down the equation first. So given this curve, find the tangent to the curve at the point xy equals to 1, 2, I think. Yeah. Right. So what do we do in this particular case? Again, like before, you just simply differentiate the whole equation. So in this case, the tangent to the curve is essentially, normally we think in terms of dy dx. Okay, if y can be written as a function of x, so that's what we do in this particular case. So over here, then we just simply differentiate the whole equation with respect to x. Sorry, differentiate with respect to x, the whole equation of equation. So let me bring this up. Oops, no, I can't do that. Sorry, I don't want to do that. Okay, I want to bring the whole screen up. So okay, so you differentiate x cubed with respect to x, that gives me a 3x squared. Differentiate 3y cubed. So y we do not know how to write as a function of x as yet, but what we can do is we do a chain rule. So you differentiate this term with respect to y first, and then differentiate y with respect to x. So that will give me minus 9y squared. Okay, and then you differentiate with respect to x, then I have dy dx. Similarly here, differentiate xy, so I keep the second factor constant, then I just have y there, differentiate x with respect to s just gives you 1, and similarly for the other one, so I keep x and then differentiate y, and then this is just constant, so this gives you means 0. Okay, so uh, it looks okay. If I want to find a different what you call if I want to find what dx in a much more general fashion, it's still complicated because there's a y term here which we do not know what it is as a function. But luckily we are asked to find the tangent to the curve at a particular point where the points are saying that you have x equals to 1, y equals to 2, and you have seen the earlier example where once you put values in, it becomes easier. So let us just do that, substitute values. So x is equals to 1, so that I have 3 1 squared. And then y equals to 2, so I have 9 times 2 squared dy dx, which we do not know what it is, plus y, which is 2 here, plus x, which is 1, and that's dy dx equals 0. So then you can simplify the equation. For example, if you write down what dy dx is, this will give me, I think, 3 plus 2, 5 over 35, which is coming from here. Sorry, 5 is from there. Where's the 35 comes from? Oh, yeah. It's minus 36 plus 1. Okay, so that gives 35. So yeah, I got the answer right in front of my eyes. So that is 36, that is 1. So you take the difference between the two, so I get 35. And okay, this you can simplify to 1 over 7. And remember, this is just the slope. What you need is, okay, I didn't mention it before, you want the tangent as a line. Okay, so what is the line? The slope we already have, but what is the equation of the line? Well, you are given the point, so the point is when y for y is equals to 2 and x equals to 1, so that means if you take the difference between the two, this has to be equals to the slope. Okay, so in other words, what do you get? Essentially, I think, yeah, so you simplify this, you should get x minus 7y plus 13 equals 0. Okay, so that will be the equation of the tangent line. Okay, so that is again pretty simple for us to do. So now we are going to go a little bit more advanced, where you have multiple variables instead of just single variable in this in this equation, for example. Then we have, if you think of y to be the dependent variable, then the only independent variable will be x. So now we can start to generalize this idea to involve more than one single variable. So let me just clear this whiteboard first. So that, it goes into a new slate. So here is the other section, which is again, what do we do here? We are going to do a lot of chain rule. All right, how should I begin this? Again, let's recall what kind of problems that we had earlier, which is simpler than the one we are going to discuss now. For example, earlier we had z as a function of x and y, and then x is a function of one single parameter, and similarly for y. And this is quite simple for us to do because then everything falls back to this parameter t, so you can find out what dz dt easily is. But now let's generalize this. Generalize. So instead of x as a function of a single variable, here let x to be a function of two variables, and similarly for y. So then one can ask, okay, in this particular case, previously we only had one option to find, well, with respect to this single parameter here, we just have, we need to find what dz dt is, for example. So here earlier was calculate dz dt. But over here, since there are two parameters, then what really you want to find is dz dx, sorry, ds and dz dt. When I say d, I mean the partial, okay, because there are two different variables. So let's look at again using examples to actually demonstrate how to do this. So again, I'm just taking this all from the book, so actually I have time to construct my own examples, but the main point is to get the steps in order. So in this case, given z equals to x times y and x equals to sine s plus t, for example, and y is s minus t. So how to find partial z, partial s, partial z, partial t? Well, one should start, this is just a matter of constructing the steps to find the partial derivatives. Okay. Later on, once you get familiar with it, then you can actually forego some of the steps. So here what do we do? So what we do here is to write down differentials. Differentials of what? Of all the equations that we have. Okay. So in this case, we have three different equations. One is for the z, then the other for the x, and the other for the y. So let's do that. So the first one, dz, okay, is given by y dx plus x dy. Okay, so just taking the differential of each variable. Okay, and then for the second equation here, dx, and then you have a sine of this particular variables s and t. So you take the function for differentiation of the function first. So you have cos s plus t, and then remember you have to also differentiate the variables inside here. So that will give me, or differentiate, when I say differentiate, I mean take the differential of each of the terms. So here, taking each of these terms, so I will have ds here, and then the other term will be dt. And the last one is quite easy. It's going to be ds minus dt. So what happens over here, if we look, remember our objective is essentially to find these partial derivatives of z, okay? But over here, what do we have? We have this in terms of x and y, okay? And also the differentials of the variables, dx and dy, okay? So, but dx and dy has already been expressed in terms of s and t. So what we can do is to substitute this into the differential. Again, this is some of the steps you later on you just simply ignore and you do it automatically. So substitute dx dy into dz, and that should give me the following. Let me just pull it up again. So I will just write it down first. Y dx is that, so cos s plus t times ds plus dt, and then x, which is sine s plus t. Do I want to do that now? Or yeah, maybe I don't need to do it. So let me just move that. So I just keep the x there, and then dy is ds minus dt. Right. So now one collect the terms involving ds and collect the terms involving dt. So that should give me the following: y cos s plus t plus x ds plus y cos s plus t minus x dt. Okay, recall what do we have in terms of partial derivative. Partial derivative is when you have two variables, two independent variables, you keep one of the independent variables to be constant, and then differentiate the other variable. Okay, so what do we do in partial derivatives? The following. For example, consider s is constant. So what does it mean by having s is constant and then t will be varying? So that means ds equals 0. Okay, so if ds equals 0, this term for dz will vanish and you only have this particular term. So in that particular case, then okay, let me just write that thing down. dz equals to y cos s plus t minus x dt. So this is a differential of z when the case s equals to constant. So in other words, if I differentiate with respect to t, partial differentiate, then you really have this thing to happen. Okay, so again, you can do the other one. Similarly, right, t equals constant, then dt will be equal to 0, then I can almost immediately write down what the partial derivative is with respect to s, which is going to be equals to, let me see, where is it? Yeah, y cos s plus t plus x. Okay, so take note of this. And compare in the thing that we have over here. So if I do that, I can see almost, okay, really your dz, this now, your dz is really what? Your dz is simply dz d partial z partial s ds plus partial z partial t. So most of the time we'll be able to just jump into this particular equation without going through all these intermediate steps. Okay. So in other words, this part will sometime what you call become automatic. Okay. So given your differential z, for example, given here, then I know immediately that this is partial z partial s and this is partial z partial t. Okay, so that's and that is going to be very useful, particularly when you do things like in statistical mechanics, where you have all this changing of the thermodynamic variables, and and this can be one set of physical law can be turned into another set of physical law. So these are things that one can actually do. So okay, maybe I should write that down. So here, the gist here is what have we done? We begin with z as a function of f x y, okay, and turn it into, well, we did not quite solve the z in this particular case, but you could, if you want to, turn this into a z as a function, a new function of s and t. Okay, so these are useful things for us to do in useful things that one can actually do in physics, because sometimes you want to go from one set of variables to another set of variables. There are some other things. I'm not sure whether I want to do this all. Let me think a bit. Or maybe I do. Okay, because I need to give you a kind of shortcut. Okay. So let me clear this thing up. I don't want to have all those dragging. So so let's look at another example. Example here, you are given this function u, which is a function of three different variables: x squared plus 2xy minus y log z. So you can see now there's x over here, there's y, and also there's z there. And x is given in terms of another two variable. So this is s plus t squared, y equals to s minus t squared, and z equals to 2t. So again here, find partial u, partial s, partial u, partial t, which is not in the original expression of your u. Okay, your s and t does not appear in these terms. Okay, so what do we do? So again, just the same thing like before. Take the differential of h. So for the case of dx, let's do the simple one first. Okay. So here I would have dx equals to ds plus 2 dt, dt, dy equals to ds minus 2t dt, and dz here is 2 dt. Okay. But remember, what you want is partial u, partial s, partial u, partial t. What do we want in this particular case? I want to take the differential of that equation on top. So the differential of that is going to be, okay, this is a bit long, 2x dx plus 2y dx plus 2x dy plus, oops, minus sign, minus log z dy, and then that is taking the differential of that, keeping that, and then I need to take the differential of that. That gives me minus y over z dz. So now what one can do is to collect the terms of dx dy. Okay, so let's do that first as a simplification. So I get 2x plus 2y times dx, and then plus 2x minus log z dy, and then minus y was z dz. Okay, but now what do we have here? We have your dx dy dz, which is already written on top here, so we can substitute those. Let me just write the whole thing down. It's going to be long. So over here, so what is your dx? Your dx is ds plus 2 dt. dt, how much time do I have? 9 more minutes. Okay, just let me finish this. Plus 2x minus log z ds minus 2t dt, and then the last one is just minus y over z 2 dt. And again, you can collect all the terms with respect to ds and collect all the terms with respect to dt. What do we have? I'm just going to write down everything first. Okay, so now if you remember, if this is du, I should be able to identify the following. This is going to be du partial u partial s ds plus partial u partial t dt. So essentially now we can, this thing is that, and this thing is that. Okay, so I don't want to write it down. Okay, so one has already the partial derivatives of that function u with respect to the implicit variables of s and t. I have about 7 minutes left. Okay, sometimes what happens is one would want the case where only one of these implicit variables to be varying and the other one is constant. This often happens also in physics. So in this particular case, what you want to write is to say, okay, let's here consider as constant and find out what UDT is. Okay, so what do you do? I already have the total differential for you in the book. So if s is constant, I just simply ignore this term, okay, that which becomes the s equals 0. So that means over here, this implies the s equals 0. So I already have du, and to say that s is constant, normally this is given a subscript s to say that s is kept constant, and essentially this will just give me this whole thing here, which I can write as, I'm going to simplify this thing. For y t plus 2 t log z minus 2y over z. Okay? I'm just rewriting everything. What did I do? Oh yeah, sorry, I've already cancelled this thing up. Okay, so finally, oh, sorry, I've forgotten the t at the back. Finally, then you get partial u, partial t is equals to that. Okay, but remember, this is the kind of symbolic notation when we try to find the differential given a particular variable is actually kept constant. Okay, and that is going to be useful, for example, again in statistical mechanics, which I'm teaching also this semester. So it's another 4 minutes left. I don't think I can finish this, so I'll probably continue. So we have this replacement lecture on Friday, right? We start at 3 p.m. Are you still with me? Okay, great. So we'll continue this on Friday, and then hopefully we finish at least a substantial amount of the current chapter 4. So let me take the attendance here. I'll be giving your not first assignment, second assignment soon. I'm just trying to pick out the right questions for you to practice on, and I will upload it by today. Today we have problems on Putra Blast, so let's see how it happens for the rest of the day. So that's done. So I think that's all for today. Thank you, everyone. Okay, bye.